Hello everybody, Mr. Hasty here. So today we're going to be talking about gases. Chapter 13 is all about gases. We're going to start with something called the combined gas law. We'll talk about why it's called the combined gas law here in a second. One of the things we alluded to last chapter is that there's a relationship between pressure, volume, and temperature. And for gases, basically, we can always compare the state of those three things to as one changes, the others change in very specific ways. So the combined gas law is a relationship between those three concepts. So the formula for the combined gas law is the pressure of gas 1, or the gas at the first state, times the volume of that gas divided by the temperature of that gas is going to be equal to the pressure after the fact times the volume after the fact divided by the temperature after the fact. So let's take a quick second to discuss what that means. It means if you take a gas and you change its pressure and its volume, change its pressure to a new pressure and its volume to its new volume, there is a very specific temperature it's going to change to. And we can take the relationship of the starting values, the pressure 1, V1, and T1, and use those to find one of the missing points, either P2, V2, or T2, in the situation. Now, real quick discussion of units. So when we talk about units here, the units for pressure and volume can be anything that measures those values. So volume could be listed in cubic meters, cubic centimeters, in liters, in gallons. It doesn't matter. And pressure could be measured in torr, millimeters of mercury. It can be measured in atmospheres. It can be measured in kilopascals. It does not matter. The reason it does not matter is because there is a ratio. And as long as that ratio is in check, it doesn't matter what the units are. Temperature, on the other hand, is a bit different. And the reason for that is we normally measure temperature in degrees Celsius. And the problem with that is that you can have negative degrees Celsius. For instance, water freezes at 0, so you could have ice that was at negative 10 degrees Celsius. And negatives tend to throw this formula off. So we have to convert everything to units of Kelvin. Now remember, we say Kelvin and not degrees Kelvin. So the only unit that's really required is that all temperatures be in Kelvin. So if you remember, the formula for transferring from degrees Celsius to degrees Kelvin, your temperature in Kelvin, and there is some extra decimal points in here, but we're just going to say it's 273 plus your temperature in Celsius. So just take your Celsius temperature and add 273. Now if you remember, degrees Kelvin don't have negative numbers because they're 0 degrees Kelvin, or I shouldn't say degrees Kelvin, but 0 Kelvin is called absolute zero. It is a hypothetical point. Looks like I wrote okay, but it's 0 Kelvin. It's the point. Now remember what temperature measures. Temperature measures the average kinetic energy of particles. It's the point where all particle motion stops. So we can't actually reach 0 Kelvin here, absolute zero, because we've in a laboratory setting we can get very, very close to it, but we can never fully get to it because there's some theoretical constraints which suggest that we can't ever get to absolute zero. So the only thing we're going to remember about units is that temperature must always be in Kelvin. So why is it called the combined gas law? Let's look at that. All right. So the reason it's called the combined gas law is it was actually based off of 3 laws that came before it. So the first of which was Boyle's law. Now, Boyle is the name of the scientist who discovered it. And what Boyle found out is that at a constant temperature, sorry, I'm having some difficulties with my typing today, so it's going to be a little bit slower. At a constant temperature, he found out that the pressure and the volume vary inversely. So his formula looked like this. It didn't have anything to do with temperature because he held it at a constant temperature. That means he made sure that the temperature in his scenario did not change. And these have what are called an inverse relationship, or a direct, basically, as one side goes up, the other side must come up as well to compensate. So if the pressure goes down, the volume has to go up. And that's an inverse relationship. As one of them goes up, the other one must come down. And that was Boyle's law. Charles' law held that the pressure was constant. So the pressure there was constant. And so they didn't consider pressure in these situations. And so holding temperature constant is pretty easy. You can just make sure the environment you're working in doesn't change temperature, right? Maintaining constant pressure is a little bit trickier. That is oftentimes done by making sure that the amount of gas particles in the environment does not change. You have to have a very, very closed system. And his formula looked like this. Charles' law was V1 over T1. And again, temperature still has to be measured in Kelvin here. It equals V2 over T2. And this is called a direct relationship. As one comes up, the other one has to come up to compensate. So if your volume goes up, if your volume doubles, your temperature has to double. And then Gay-Lussac's law was pretty much, if you haven't guessed yet, it was doing it at a constant volume. And to keep gas at a constant volume is a pretty easy task. You just need it in a container that cannot fluctuate in the amount of particles in, the size of the particles where they take up space. So like a glass jar. And his formula looked like P1 over T1 equals P2 over T2. And if we look at this, we're not going to mess around with all these different formulas. We're just going to use the combined one, which is P1V1 over T1. This is the formula I just gave last slide. P2V2 over T2. It's kind of fun to say. P2V2 over T2. And basically, if one of these are held constant, we just remove it from the equation. So in Boyle's law, we have a constant temperature. We just take temperature out of the equation. Because the temperature is constant, it's not going to change anything. Similarly, for Gay-Lussac's law, if we have a constant volume, we just remove volume from each side of the equation. And we use the equation like such. So it's pretty easy to find the law we need using the combined gas law. Let's do some examples. Okay, so example 1. A balloon contains a volume of 1.89 liters of gas. Let's call that V1. Now, the units for your V's don't matter as long as your units are the same. 1.89 liters. Okay. Assuming the pressure remains constant. So we have a constant pressure. When we go to use our formula, P1V1 over T1 equals P2V2 over T2. That's a terrible P. Pretend like it's good. We're going to eliminate, if we're at a constant pressure, we're going to eliminate pressure from both sides of our equation. What would the volume of the balloon be? So we're looking for V2. That's the thing we don't know. if the temperature is raised from 25 degrees Celsius to 45 degrees Celsius. So our T1, now we're in Celsius, we have to convert it. Remember, to convert it, we're going to add 273 to the number, right? Because to go from Celsius to Kelvin, you add 273. So 273 plus 25 is 298 Kelvin. And remember, that's the only unit that really matters, is we got to make sure we're in Kelvin. And it goes up to 45, so T2 would be at 318 Kelvin. So we simply fill in all our info. We have 1.89 over 298 equals V2, which we don't know, over 318. And we're going to use everybody's favorite mathematical thing, cross multiply and divide. When you cross multiply and divide here, you get that your V2 is equal to 2.02 with correct sig figs. And units there, well, we're measuring a volume, and our other volume is measured in liters, so this is going to be in liters. Easy peasy. All right, now let's look at the next one. A bubble in the ocean has a volume of 0.85 cubic centimeters, so this is going to be our V1. I'm just going to label it here. Initially at a pressure of 2.34 atmospheres, so that's our P1. As it rises to a depth where the volume is 1.75 cubic centimeters, so here's a V2, what is the pressure at that depth? Now, in this, it doesn't say anything about temperature. We're going to assume a constant temperature here. So, our formula is going to look like this. P1 V1 equals P2 V2. So this would technically be using Boyle's law, but it's just a version of the combined gas law. So I'm going to plug that in. I get 0.85. So restricted to 2 sig figs right there. 0.85 times 2.34 atmosphere is going to be equal to 1.75 times V2. Now solving this is pretty straightforward. We're simply going to multiply the numbers on the left side here and then divide that 1.75 on both sides. And when you do that, you're going to get that your V2 is going to be equal to, oops, I goofed. This should be P2 that we're looking for. It doesn't change my equation. We'll just call this P2. And we're looking for P2. So we do that and we get, being restricted to 2 sig figs, I get 1.1. But what will my unit be there? We're looking at a pressure, and previously our pressure was measured in atmosphere. So this one will be measured in atmosphere as well. All right. Now let's look at one where you have to consider all three of our variables. So in this one, we have a gas at 105 kPa. That's kilopascals, so that's pressure. Let's call that P1. And 25 degrees Celsius. So we have to adjust the temperature by adding 273, and that'd be 298 for our temperature there. 298 Kelvin. Remember, all temperatures must be in Kelvin for this to work out. It's contained in a flexible container with an initial volume, we'll call that V1, of 2.15 liters. If we increase the pressure, so that's a P2, I'll just write P1 here. P1 was 105. our P2 here is a lot higher. It's 335. So that's more than triple the amount of pressure. But the temperature is lowered to negative 10 degrees Celsius. So our temperature went way down. Now negative 10, we'd still add negative 10 to 273. So our T2 here is going to be 263, because negative 10 plus 273 is 263. And we're looking for the new volume. So it's hard to predict. Our pressure went up, our volume went down, our temperature went down. Let's see what happens. So we're going to use the full formula here. P1 times V1 over T1 equals P2 times V2. So we're going to have 335 V2 divided by the temperature there. So what we do is we just clean up there's a couple ways to do this. Most people want to do the cross multiply and divide, so we can do that. We're going to take 105 times 2.15 times 263. So we're going to clean up the top left and then multiply it by 263. When we do that, we get, and so that we don't lose accuracy, I'm going to write out the full thing, 59,372.25. And that is going to equal, we're going to multiply 298 by 335 V2, and we get 99,830 V2. So we divide both sides like in algebra, and we're going to get a second volume of